Jim's birthday on the 28th.
Okay, good morning, everyone. Today is December 17th, 2016, and welcome to the John Soppel Natural Philosophy Society Science Chat, where we talk about anything you want about science. And so I just want to remind everyone, this is sponsored by the CNPS, and I have the slide here with our website on that. And if you'd like to support us, please join us and renew your membership. And you can like us on Facebook. And as a member, you can use some of the tools that is provided by the Society. And you can participate in our conferences. And of course, the cost of this web meeting is supported by the CNPS. All right, so it looks like Eric is setting up his experiment again about
That's right.
About the photon nature of light. I think that's a very interesting question that I wanted to throw out there to everyone, which is what is the nature of light? So the controversy is that mainstream has this thing where they say light is both a particle and a wave. Now, personally, I find that hard to swallow. That's like saying some object is black and white. I don't think that can really be both ways. So it seems like Eric's experiment here is trying to contradict that idea by saying that light acts strictly as a wave.
That's right.
So I'm wondering, do other people have some opinions on the nature of light? Is it really ever a particle?
I agree. It has to be one way or the other. It's the same for particles. You know, with quantum mechanics, particles are dual, and they can be a wave and a particle at the same time, right?
And what do you mean it can be a wave and a particle at the same time?
Like an electron.
Well, I thought you said that you disagreed that something has to be one or the other, right?
Well, I'm saying that the mainstream says
yes,
particles, which I also disagree with. Particles are particles that have wave-like properties.
No.
They actually move wave-like motion, in my mind, and that was shown by Peter Beckman. How that can work, that if you impose a perturbation on the velocity of a particle, that it slows down and speeds up due to the Lenz's law, that you can derive Schrodinger's wave equation.
Now, what about the experiments that they point out? For example, I believe they have done experiments with electrons, which we do believe are strictly particles, and they've like shot these electrons through like a double slit experiment, and somehow they form a diffraction pattern,
interference pattern, right?
An interference pattern. So, and they would point that out as saying that, well, see, this is clearly a wave of behavior coming out of a particle.
Well, if there's an ether, you can show how the ether will, and the particle interacts with the ether, that this wave-like motion of the particle, can give rise to the interference pattern. But if you don't believe in an ether, it's very difficult.
Well, how does the ether cause an interference pattern? Because I would think that
it forces the particles to into the interference pattern. It interacts back on the particles.
do you have? Can you explain that a little bit further? Because I'm not quite sure how that would do that.
There's actually been some experiments with a shallow uh, kind of bath of oil, and it's hard to explain, but by
Yeah, I know that experiment. There's silicone droplets. The problem with that experiment is that the barriers are at a different level from the waves. It's a trick if you look closely into it.
but
And
it shows how if there's a medium that interacts back on the particle, it can affect the motion of the particle that makes it look like it's moving in a wave-like manner.
yeah,
And I
it
think
looks like it won't work in general. It's a very special case that's set up, and if you're not going to be able to get a wave pattern that is centered at a particle.
I think they were able to get diffraction-like behavior.
I know they had diffraction lights. It's a very special case, not a general case. It's not a general situation.
It's only an analogy at this point, but it's trying to show how a medium can give you some of the things that quantum mechanics insists you have to have some kind of behavior for.
Yeah, look, I would have to have the paper in front of me.
Yeah.
But from what I remember, it was just an act of desperation, and they did a trick where they had the double slit barriers at a different level from between where the wave was and their droplet was, and it was just cheating. So
Although that particular experiment would agree with the hypothesis that that particles can display wave-like properties, even though they are truly just particles, right?
If you add a medium.
no,
If you add a medium.
no. Particles will hold themselves together, and a wave will not. A wave goes everywhere. The ideas are mutually exclusive, and this is the nature of wave-particle duality. That it's just a model. It's a broken model, and there's something else going on.
Yeah, the ether.
The ether is there, but that doesn't answer the question for wave-particle
Well,
duality.
you have to give it the right properties, but until you until you accept the possibility of an ether, you're stuck.
Well, look, I put 16 years into this experiment to try to show the nature of light. I've just done this experiment with light. I've done the same experiment with matter as well. So it's about resolving the wave-particle duality for both matter and light. And I do have a decent answer for this. And you're not going to get the answer by trying to make particles diffract. But what's going on is an accumulation and the threshold effect to give the illusion that a particle hit there. So there's a way to see the distinction between this accumulation idea and wave-particle duality. And the distinction is this experiment that I'm trying to show. That I've been telling people about for it's about year 2001. Had this running. So I'm using gamma rays in a beam split coincidence experiment that's looking at the particle property, very specifically the particle property, and see if it holds up to what other people say the particle property of light should display. And you'll just about see it in the definition of what a photon is. Photon should go one way or another of the beam. It's the famous quote from Bohr's book, where he had this conversation with Einstein. Bohr is paraphrasing Einstein, saying, well, and Einstein would say, photon would go one way or another at a beam splitter, but afterwards it would converge and make an interference problem. There's no way to really, there's no way to see how that could happen. It's just a model, and it's always been a paradoxical model. And there've been a list of acts of desperation and 100-year-old what's going on to make that happen. First, understanding that the photon idea is just a model
Can I ask a question? Can I ask a question?
upon our experiments, that there's something else going on.
Yeah, Akimbo, you can go ahead and ask a question.
Yes. What exactly do people mean? What's the difference between space itself and the ether? Is there any difference between space itself and the ether, or are they the same thing?
Difference between what?
Is there any difference between space and ether?
I can tell you that I'm not answering that question.
Yeah, Eric's more of an experimentalist. I mean, you could ask myself or Jim that question, and I would say that the ether and space are different. Space is just a spatial dimension, but the actual ether is actually made out of, say, sub-identifiable matter particles. That's what I would say. That would be my opinion. But once again, that would only be my opinion.
Yeah, I would agree with that too. One of the biggest problems with ether concepts originally were that absolute substance or fluid that filled up all space and was completely the same everywhere, not compressible or having different density or being able to be carried by a massive body. So that that led to all sorts of problems with Marcus Morley.
But getting back to the question that Eric is trying to answer, I think that we need to be able to explain the other experiments that show that light has a non-wave or particle-like characteristics, I guess. For example,
That's right. There's the photoelectric effect, the Compton effect, black body radiation. There's a list of experiments you'll see at the beginning of our textbook that give the argument that light has to do with particles. So
Well,
that's
there's also the idea that there is no ether. You've got to be able to shoot. You've got to be able to shoot something from somewhere to something, because there's no medium to transmit a wave.
well, if light is a particle, then it doesn't need a medium, which
That's
is one of the
That's the point.
which is one of the cool things about the particle thing. You don't have to have anything from A to B to get some reaction that happen between A to B if you're just throwing something at it.
Although it's got to have all these magical properties that you can't explain, like why does it assume the speed of light?
But what about the photoelectric effect, Eric? So how do you explain the photoelectric effect as being caused by waves as opposed to being caused by a particle with a fixed amount of energy?
it's a threshold effect. That Planck's constant is a property of matter, not light. You do not have to put Planck's constant into light. I encourage all of you or any of you to look at my the theoretical part of my work, where I did a derivation of the photoelectric effect, where you do not have to have particles of light to do that. And the same with the Compton effect. I did several derivations of the to get to the equations that describe the experiments without particles. But to get to really see it work requires that Planck's constant and a few other constants are maximums. This is the difficult part of the concept. See, if you have action quantized all the time, you're going to get into trouble, and everyone else will. There's a mathematical simple trick that I did that's very profound, and it's about ratios and thresholds, and it's hard to get across just talking about it. You have to see the equation where in the photoelectric effect, what happens is a Planck's constant and the mass constant form a ratio. So you have H to M. And you think, well, there's an M, there's a whole mass there, and there's an H, there's a whole H there. But it's really not required for it to be full like that. You could have half an action and half a mass and still have the same ratio. What happens is that the ratio is conserved in the equation, and then you get to see through the illusion. Well, that's a whole mouthful, but it's about the ratios of Planck's constant, the mass constant, and the charge constant, our fundamental equation, and re-examining it, and wave-particle duality goes away. That's the theoretical part of my work. And then there's the experimental part that shows where right in front of me here, that shows how the particle property just has to fail altogether.
Now the photoelectric effect, so just to review, the photoelectric effect is that they are shining photons on metal, and they shine it at a particular frequency, and they find that no matter what the intensity of that beam is, it does not increase the number of electrons that are ejected from the surface. So the argument is that shows that light is a particle, because if it's the particle that's doing the ejecting, that that particle only has that it doesn't depend on the number of incoming particles that come in. It just depends on the individual particle having a fixed amount of energy. So the argument also is that if it was a wave, that if they increase the intensity, then that should increase the number of ejections because of the increased amount of energy that any wave can hold. So therefore, they say that that cannot be a wave, that cannot be caused by a wave. So that's the basic argument there. So as scientists, go ahead. You had a comment?
The photo is from 1905, but the photoelectric effect at that time was done with crystalline metals. And when they repeated it with the same metals, but they used the amorphous form, there was no photoelectric effect, showing that light is not a particle.
Was it that
when we made optical chips, we found that you had to have that crystalline structure for an antenna, or you cannot receive light. You cannot get light absorbed. And so all the people that make optical chips will tell you there is no such thing as a particle of light.
So by a photoelectric effect not being there at all, you mean there was no ejection of electrons at all?
When you use the amorphous, yes.
So it just doesn't work. I mean, it's because it seemed that the argument was that because the intensity of there was no relationship between the intensity of the beam and the ejections, that contradicted the wave idea of the photon. Although if the photoelectric effect didn't work at all, then I don't think that would really have anything to say about the nature of the photon one way or the other. It just wouldn't work if there was no ejection at all. I think it would be more interesting if it showed that.
Well,
You
Go ahead.
you have to have a crystal structure for it to work. That could mean that there's something else going on besides.
an antenna.
Look, there are a wide range of efficiencies on the photoelectric effect, and whether the crystal is there or not, that's not the issue. It's just different efficiencies for the photoelectric effect, and you could see it with amorphous cells or a phototube. You could see it with a phototube that has nothing to do with crystals. So you don't need crystals to see the photoelectric effect. The other thing is, if you talk about light in terms of photons, you'll end up with photons. It's best to just talk about light. And also, the same problem happens with electrons. If you have in your mind that electrons are emitted, you're just going to be lost in wave-particle duality. Think about charge being emitted, because charge has the same problem of wave-particle duality as light does. There's a problem with our language that goes along with the physics in order to grapple with this problem. That's the first thing I want to interject. But I'm talking from years of experience of going over papers and articles. I have a gigantic library here. I went through the trouble of putting together a library so I could see firsthand like the works of Planck and Bohr and Compton, their papers. What happened in the history of physics to make this wave-particle duality? And there's a sensational amount of work has been done by great people in the past on there. And but a good deal of it was in the past. Like you have to go back to 1930 to see how people were grappling with it. And they did a really they did a good job for the most part. But it hasn't changed. We've been in wave particle duality ever since.
I see Kimbo has brought up a comment here. Now, we have this controversy as to whether light is a particle or wave, but he also brings up this point that light appears to be transmitted in a transverse fashion. And I would actually have disagreements with even that as being a fact, because in continuous mediums like air or water, it's really difficult to imagine how a transverse wave could be transmitted through something like that. And if we are to believe that light is transmitted as a wave in a medium, then we have to explain why we see something that tells us that light is a transverse phenomenon rather than a standard longitudinal, like a sound wave phenomenon. So did anyone have any opinions on that? I mean, does light truly transmit in a transverse fashion? I mean, I would disagree, but what do other people have to say?
There's a simple experiment that you could see that they have at the exploratorium. There's a simple experiment you could do with microwaves, where you have like an oven grid of wires going up and down, and it conducts electricity. And so polarizations, directions are transverse. It's very well established that there's a transverse, that light is a transverse wave. So, if, to get a good handle on it, there's that experiment with microwaves I mentioned to convince you.
Well, I've seen like interesting experiments with microwaves. You just like stick a candy bar in a microwave, and then you can see that it only melts certain spots. Although I don't think that convinces me that light travels in a transverse fashion.
No. I'm talking about a set of wires that are transverse that will conduct the charge transversely. So it's you have a set of wires going up and down. Wave is coming towards you, and you'll see the polarization of the wave will conduct in, but if you twist the wires, then it goes through. So you could see the
Let's see, we got someone's dial tone going on here. Okay, I think that was.
I think fairly established on principle that when you have polarization, this is an indication of the nature of the wave. You don't have polarization with longitudinal waves. So once you have, since light displays polarization, I think it's fairly not controversial, like Eric said, that light, by virtue of that polarization property, is a transverse wave.
Well, let's take a look at polarization. So, like we have polarizing lenses, and so you put a light bulb behind two of those, and if you orientate the polarizing lens at 90 degrees, it completely blocks the light. Now, this is kind of like the analogy of a rope going through a picket fence, and that you wave it up and down, and it goes straight through the picket fence. But if you orient it the other way, then it will completely block the light. Now, I personally find that to be a completely naive and incorrect way of looking at the picture there.
Well, that's why I brought it up with microwave, because it really is light. It's electromagnetic. You don't need to do some analogy with ropes or whatever. You could do the experiment with electromagnetism and bring it out to a macroscopic scale so you could see it firsthand.
The problem is that your concept of the ether, maybe there's different properties to ether that could support this transverse.
Yes.
And in fact, it's not just a simple transverse. It's transverse with the electric field and the magnetic field 90 degrees out of phase.
Well, see, the problem is that for etherists, I don't think you can come up with a property like that would allow that kind of polarization to occur. But this is how I see it. I mean, my opinion is that light is not a transverse wave phenomenon, that it's strictly a longitudinal ordinary compression wave phenomenon, but that it's highly localized. And this is what makes light different from every other kind of longitudinal wave, as in that it can come in a very, very small packet, like a string of billiard balls. And generally, once emitted, maintains that particular shape. So as it flows through the ether, it's just like this string of billiard balls that the wave runs through it, and it, generally speaking, doesn't dissipate. This is why, like laser light, we see laser light, generally speaking, does not dissipate. It goes straight, keeps on going straight until it hits something. And that's a very unusual property.
No, it's not true. Laser light will spread transversely just as much as other light. And the Maxwell equations are very well established for this transverse wave thing.
You don't
I
accept
don't
Maxwell's equations?
Maxwell's equations.
Well,
Uh,
that brings up this whole other thing about light being this it's exchanging between the electric and magnetic field. If you've ever seen that picture,
Yeah.
and I find that completely unbelievable.
Franklin, can you hear me? It's Duncan Shaw.
Yes, Duncan, go ahead.
Thank you. I was interested in your example of a string of billiard balls because quite obviously those are transverse, at least I think, transverse waves going through the billiard balls. But there's got to be, pardon me, longitudinal, but there got to be transverse as well, because when a billiard ball, albeit a very hard object, is squished one end to the other, its sides have to bulge. It seems to me that that sort of reasoning is equally applicable to ether. If you think of ether as being made up of ether cells that are flexible, and if you push them from one end to the other, they've got to squeeze at the side. If they squeeze at the side, they've got to be sending out uh, uh, energy into their neighbors at their side. So they're really doing two things at the same time. And it seems to me the key to all this discussion is if you think of ether as being made up of cells, you've got the force that goes straight ahead, but you've also got the force that goes off to one side because if they're flexible, they've got to squeeze in both directions. Do you follow what I mean?
Not exactly. I mean, you can take a laser beam and point it at the moon, and we do this, and it maintains enough coherence to go all the way to the moon and back. Now that's very unusual. There's no other light source we could use that could actually do that.
No.
And that seems to be, we couldn't use a sound wave we couldn't transmit a sound wave like that for any distance, but we can transmit things like laser light like that. So I'm just saying that's a unique property of electromagnetic radiation, as far as it being a wave.
Yeah, I see what you mean. Can that be a product of a polarization in the sense of a force polarizing a medium, making it its particles operate and situate themselves in a straight line? Like, going back to the billiard ball, you get practically nothing at the sides. I'm just saying there's a little bit at the sides when you have that force going straight through the line of billiard balls and it pops out the one at the end.
Well, I think I would argue that, let's go back to the picket fence analogy.
Mhm.
So instead of a single picket, let's make a row of 20 picket fences right behind each other, right?
Mhm.
Now, if you were to look at that, or if I was to take a laser beam, let's say, and I were to shine that laser beam at that set of 20 picket fences, I mean, basically the only way that laser beam could actually make it to the other side is if I was shining directly through the gaps in the pickets, right? I'd be pointing it right through the middle, and I could point it up and I could point it down, but as soon as I went from side to side, it would be completely blocked, right?
Mm.
So that's a kind of a polarization effect.
I doubt it would be completely blocked, because if you've got some transverse transfer of energy, you've got ways and means for that energy to go back and forth between the cells and weave its way around some of the picket fence, like the two-slit experiment. How can you explain the two-slit experiment without there being some side to side and front to back transfer of energy between particles or cells?
Well, I think that is usually explained as being, I mean, that's consistent with longitudinal transmission of light. That is just a longitudinal wave.
Well,
But we're talking about, how do you explain polarization?
oh,
So-
I become polarization in many different ways, but one of them is an electromotive force forcing particles to assume certain positions. For example, the magnetic field around the Earth, the tremendous well of energy that's of electricity or electrical energy that's in the Earth is transferred around the Earth to the outside of the Earth. Particles, I'll call them ether cells, are forced to assume positions, and when they assume positions, any magnetic needle that's within the vicinity of what's happening there is going to take up the same plane as the particles that have been forced into that plane. So I think of polarization as a forced configuration of a medium, which is a way that Maxwell considered polarization.
Well, Maxwell did not consider particles. His was purely a wave theory, and you're not going to be able to explain wave interference with particles.
Sorry, your voice is not coming through.
Thank you. You were describing an ensemble effect. The ensemble, what's going on with wave particle duality is not happening. It's not about an ensemble effect. You have this one at a time happening, where you have clicks on your detectors going, say, hey, there's a detection event, and it's at this one at a time level where you'll still get an interference pattern. That's the nature of wave particle duality. What you were just describing with your compass needles, and many people try to do it. It's an ensemble effect. That's just missing the point altogether. No, wave particle duality happens with the one at a time. So duality. There's no how you're going to have particles being guided by wave. There's another way around it that I'm trying to get through. That I'm trying to show that I've resolved with experiment.
Yeah, you're breaking up there, Eric.
That the particle properties, its particle properties, you do not have to have particles to have a particle property. You can have thresholds that give the illusion that a particle showed up. That's the key. That's the way to get through this problem. And I'm not just blabbering. I'm talking from experiment that's backing me up.
Yeah, I've always wondered about these so-called single particle detections of electromagnetic waves. You know, they have these germanium sensors. Like I believe you're doing that with your experiment. You're measuring gamma rays, right? And
That's right. There are pulses that show up on the oscilloscope that say, and people will look at those pulses and say, "Oh, a particle showed up there." No, the particle goes click, pulses. Well, you'll see those pulses happen with light detectors as well, from photomultipliers all over the spectrum. You can get detected between pulses, but it doesn't mean that a particle was pre-packaged ahead of time. There's something going on in matter and in the way the detectors are put together to give an illusion that a particle hit there. And so the experiment I have here is about seeing through that illusion.
yeah, because I would think that it would require incredible efficiency if light were really actually an individual photon. and an individual photon hit these detectors and caused a click, that it would just seem that like it would take like 1,000 wavelets in a wave packet to actually trigger that thing, and that's what you're actually seeing. You're not seeing an individual something hitting the detector. You're seeing like thousands or maybe 10,000 wavelets hit that detector before it's enough to trigger the sensor.
That's right. Well, look, there's a lot of confusion here. To try to describe light in terms of photons, that's a big mistake. And let's be clear. The wavelets are not photons. Wavelets are just waves. And you're right. It would take thousands of wavelets to come together to make a click on any detector. So right away, you're into duality. And you're able to see, oh, there must be something else going on. So what I'm saying is going on is that the wave energy accumulates to a threshold. It builds up, and then it goes click, and that's in our detectors. And it's a threshold effect. So the thing to do is find an experiment that will show the distinction between the threshold model and particle models or quantum mechanics. The model of quantum mechanics doesn't answer the question. Quantum mechanics just says there's a probability wave that guides where the particles go. Well, that's wave-particle duality. So we want to show, how does quantum mechanics fail? This experiment shows that. But there are a few things you need to understand, that I'm dealing with a source that emits one at a time. And there's an experiment that we do to see that. So it's not an ensemble effect. We get a one at a time emission of H nu energy. People call it the photon energy, but I really don't like calling it photons. You have to have a one at a time emission, and then you see it goes in two directions more often than chance.
How can you have if light is strictly a wave, how can you have a one at a time emission?
It is emitted quantized. There's a whole H nu that's emitted from an atom in spontaneous decay, but after it's emitted, it's not held together anymore like a particle. So there's at the instant of emission, there's something quantized about it.
I think it's like, I think it's like ringing a bell. So you hit the bell and it gives off sound for a certain period of time, and the energy is defined by the resonant frequency of the particle that you're hitting.
That's right. That's right. It is like hitting a bell. The hitting is an initial amount of energy, and thereafter it spreads like a wave.
Well, I'm saying that the particle vibrates like a bell vibrates, and it's emitting electromagnetic waves at that vibration frequency, and the intent and the the height of the intensity of each wavelet of each wave wavelet.
There's a sinusoidal, wave. Let's just call that a wavelet. I mean, are there going to be multiple of those, or is there going to be a single sinusoidal wave and that's it? It's going to be an up and down, and that's.
Well, no, it's giving off this pulse of electromagnetic waves that decays over time, but the aggregate frequency of the it's like a chirp because of the pulse has an average frequency to it. But I'm not explaining myself very well. I'm sorry.
So Eric, is it like a bell ringing where it decreases in intensity as time goes on, or is it a single sinusoidal wave?
It's a sinusoidal wave that will decrease intensity as it spreads in space, just like a classical wave. But the initial emission is quantized. It's like taking a cup of water and throwing it all over the place. You're starting with a cup worth of water, but afterward it spreads. But then you have to see the same, you have to see the opposite happening. The opposite happening is when it accumulates. It's like singing into a wine glass and hitting the right note and making it break. Well, if Ella Fitzgerald was singing the right note and making the glass break, you'd say, "Oh well." If you didn't see the, if you didn't understand it was sound, you'd say a particle hit there to make it break, but it just reached a threshold. It just built up in intensity, and then the glass broke. But you did not have to have a particle hit there to make it happen. So there are threshold effects that you have to, that one can apply to both emission and absorption to see through the illusion of particles and also understand that it's waves. And that's the model I'm using. The model is more elaborate that I tried to mention before about ratios of constants, but it's essentially that. It's a threshold effect. Threshold model.
I'd like to say something on that point, if I may. I'm not understanding your model, Eric, when you say an atom is emitting some kind of electromagnetic wave. Isn't it directional though? Or if you ring a bell, it radiates spherically. So in your model, the way you describe it, it sounds like you could set up multiple detectors all around that emitting atom, and all the detectors would detect that emission rather than just one detector. If only one detector detects that emission, then it's more localized and directional and not like a bell, which would radiate spherically.
Well, it's not a single particle with a single detector. It's an aggregate effect. You got to have like a bunch of these pulses combining together to at the right instant to pass this threshold to excite the receiving particle enough to break the glass essentially.
Well, Bob Gray has a comment in chat here. He's just pointing out that the energy from a bell is not directional. However, the light is. I mean, whatever this phenomenon is that creates lights from EM from atoms seems to be very, very directional.
Well, look, the degree of directionality is a function of frequency. There are equations for that people know about. There's a Gaussian distribution as to how much the wave falls off with angle. It's a function of wavelength. So that's well understood. There's spherical waves, but you can have it initially directed, and it falls off when you get to larger angles. That's understood in optics. That's not really the problem.
Are we talking about a dipole as well, which does have directionality to it, or even a quadrupole? Even a quadrupole, or various for more complicated atoms. They're not. It's not ringing just like a spherical bell. I mean, even quantum mechanics has these different shell patterns that they display with lobes.
Right. Look, you can have an initially directed wave, but it's not perfect. You look at the profile of a wave, of the energy distribution, and over to the edges it falls off. It's a simple equation that shows the profile as a function of wavelength. But it still spreads in spherical wave fronts. But it's not whole spheres all the way around. You can direct it to go in one direction. And at the same time, it spreads transversely. So you can aim a laser at the moon and it'll still spread transversely. There's no perfect beam of light that'll fold itself together and stay parallel.
That's more of a function of focusing.
Although if light didn't hold itself together when we look up into the starry sky at night, if light diverged even a tiny bit, I think that would cause the night sky to look like a gigantic fuzz and not the tiny little points of light that we perceive. I mean, that's pretty incredible that light can travel like, 1 billion years and maintain its absolute arrow straight path to Earth while doing so, right?
Well, actually, that's the light is actually being emitted from a star in a spherical distribution. It's just that when we detect it, we're looking at.
I mean, I guess that kind of goes to this question of whether light is a particle or a wave. So if light were, say, a particle from that distant star, then we could easily see how it could travel all the way for 1 billion years in a straight line until it hit the Earth. Whereas if that particle was a wave, then it would be like a spherical distribution all the way across the universe, and then how could it possibly reach us in one piece?
It's as it spreads out, its intensity falls off as 1/r². In every direction.
I've had this argument before. So you can simulate starlight in the laboratory. You can attenuate a light down to the level of what starlight would be in the laboratory. You could have this low intensity, and then you'll still see it with your photomultiplier tube doing clicks, and you'll still have interference patterns. So there isn't any problem about it being so weak and having it need to hold together as a particle. So I think that's what your problem is. You think it gets so weak that it would just go away. Well, no. You can make it that weak in the laboratory and see that it doesn't go away, and you can still detect it.
Well, I think this goes to, for example, when they, I don't know, do positron-electron annihilation, they say that creates 2 specific gamma rays. And to say that, I mean, that sounds an awful lot, that sounds awfully particle-like. But to me, that could also be interpreted as creating 2 very distinct wave packets heading out in opposite direction. I mean, that's why I introduced this concept of light as being like a packet, being laser-like, that when you emit light, that it maintains its coherence in this wave packet. But it's not to be generally confused with light that comes off, say, a candle. Now, candle light is being generated by like gazillions of photons in every which direction, and that's called non-coherent light. And that kind of light definitely emanates in a spherical fashion. But there's something special about laser light being a coherent beam that locks it into very strict spatial sense that's different than the kind of light that you get from your ordinary incandescent flashlight. So I think there's some difference that has to be considered there. I mean, we can still get diffraction effects out of either laser light or flashlight light. I mean, you can get diffraction effects out of just using a regular incandescent lamp or sunlight. So I don't think that is necessarily a restrictor, but there's something special that needs to be considered about that nature of light. So, for example, I was bringing up the how can polarization happen? And I'm saying that if you can consider light like that, like it's like like a broomstick, basically, right? A broomstick has a certain length, certain width, but it remains like a solid stick. And so if I were to throw a broomstick through my row of 20 picket fences, the only way it's going through is only if I throw it basically straight through. Now, if I then took another set of 20 picket fences and I oriented it 90 degrees to the first one, I could see that when I try to throw the broomstick through there, it might make it through the first filter, but would definitely be completely blocked by the second filter, which is going the other way, right? So you got a filter goes this way, add another filter that goes this way. Well, that blocks it 100%.
Yeah,
So
but you're not going to get broomsticks to cancel out or reinforce. Particles just do not act like waves. Particles
no,
don't cancel themselves out.
but
waves do.
But I'm saying that as they travel as waves, they maintain this broomstick-like coherence. The light waves themselves is just a wave packet, still consisting of waves. So you can individually interfere those two together. I'm just saying that I'm trying to say that.
No, it really doesn't work. The waves have to be much wider. The wave packets, the waves are spread over wide ranges of slots in diffraction experiments. You're not going to be able to make wave interference where it goes through one hole or the other. It goes through all the holes at once in order to get the interference patterns.
Yeah, but I'm trying to argue that that's kind of the nature of the source of the light and not the light itself.
No, it's the nature of light. Nature of light we're experimenting on with diffractions and mirrors and interference patterns.
Yeah, if you talk about incandescent light, you're talking about a lot of different molecules emitting individual packets that all add up together. And that's why it's incoherent, because they're all behaving incoherently, because they're like in a gas. With laser, the crystal is canceling out or adding together to form the coherent beam. It's not the nature of it's not the nature of the light. It's how the light is being generated, and it's not a single particle phenomenon necessarily. It's a statistical grouping of particles. It's like a black body source.
Well, I would think if I was doing a double slit experiment and I was using my standard diode laser, that if I aimed the laser at only one slit, that the majority of the light would only come through that one slit. I mean, it just wouldn't work. I'd have to put some kind of diffuser on my light source to make this effective.
Well, you're not going to see interference. You'll see diffraction. You're just shining through one slit.
You'll still get wave properties with one slit. You'll have an interference pattern with one slit or many slits, but it still needs to be analyzed with waves. It just doesn't work, particles going through little holes to simulate what light does.
Well, I mean, you bring up an interesting point there. Is like, have you guys heard of this? It's called single slit diffraction, which is that if we've all heard of double slit diffraction, but what floored me is that if you just use a single slit, you still see these interference fringes. So how can that be? Wave or not wave, particle or not wave, how do you get interference from a single slit?
I would suggest there is a way that it can be done. And the way I suggest is that if you consider ether as made up of flexible cells that have elasticity, the collisions between those cells can go any direction, and they can be brought back into focus, is quite obvious, and they can find a way around one slit or two. They can be guided by one slit because they're going to be striking the edges of that slit, and that's going to cause them to turn, as it will cause a ping pong ball or anything else, as as it hits that to turn. Your example of light going arrow straight from a star to us over billions of light years, in a way, is a good example, because I don't think it shows that there are particles going from A to B. I think it shows that there is energy going from A to B, because if it's if these are direct line particles over billions of years, they are going to hit something. They have to. There's just so much tucked into our universe that you can't send light over billions of years by a particle that goes directly from A to B. There's always something in its way. We know that starlight gets stopped when you raise your hand and you look behind your hand and you can't see the starlight anymore. It stopped. Your hand has stopped it. And if it's particles coming, they've got to be stopped. So you got to find another explanation than direct flying particles from A to B. And that, in my suggestion, is where you bring in flexible cells that collide with each other. And just to go one step further, if you got flexible cells that make up a medium, the flexibility of those cells, how can I put it, allows the light to go in many directions because the collisions go in many directions. It allows the light to be diffused as it goes through one slit. It allows for different kind of confusion as it goes through another slit, exactly the same as water or air. You get the same collisions, and the collisions can work their way around barriers, whereas direct transfer of particles cannot.
Okay, so let's get back to this question of single slit diffraction.
Mm-hmm.
So I would think that if you're doing this in a wave table, and if you have a single slit open, you put a wave through there, that you would just create a spherical wave out of the single slit that would just go and hit the screen, and there would be no interference at all. That would basically be the expectation for a single slit. However, we don't actually see that with light. You do that kind of experiment, and we do see interference patterns show up. I believe the interference patterns kind of depend upon how wide the slot is, or maybe even how deep the slot is. So things like that are giving us clues as to how that particular kind of thing happens. I mean, my personal opinion is that it shows that the wave is interacting with the edges of the slit, and as it goes by the edge of the slit, it is creating its own waves, and then that is what we're probably seeing causing the interference, that both the edges of the slit are creating their own waves, and then that is what we're seeing. But that only really happens with light phenomena. You would not see that in a wave tank. I put that out as a possibility. One other thing I put out as a possibility, that if space is made out of an ether and space is quantized, then we get in kind of this Lego brick world, where as the light goes past the edges, it can't freely move in a completely spherical fashion. Then when it hits the edge, it has to go either in one slot or the other slot, or there's probably only like 3 or 4 choices it could possibly take when it hits the edge, if we're in Lego brick land, and then that itself would cause the kind of interference that we see. So that's another thing I would suggest as perhaps evidence that space is quantized, that's really the only way we could get this kind of single slit diffraction going on. Let's see here, someone's making a lot of noise. I don't see who that is. So
But
Eric, what do you think?
don't see the problem with a single slit diffraction. It's very well understood by equations in optics class and the ripple tank. You can get the same thing happening with water as light with a single slit. I just don't see I don't see your problem. You'll have interference patterns just with a single slit. But whatever is going on, you're not going to get the same property as if you were throwing a bunch of particles. And again, these cells going on, you're not going to see what's going on is not an ensemble effect where there's many cells. The wave particle duality happens where there's one cell at a time, one H nu at a time, one emission at a time, and then it interferes. That's the problem with wave particle duality. That's the problem to be resolved. And it's been 100-year-old argument. There are people who agonize over it that long. We see these particle properties and wave properties. Well, what's going on? So here I have an experiment to show it. To show I'm taking what's the most particle-like light, gamma rays. Now you mentioned annihilation and all that. I've done that experiment. I'm able to see gamma ray annihilation going in opposite directions and coincidences. If you take gamma rays, which everybody thinks is particles, and I make it go splitting in a beam splitter or something analogous to a beam splitter, one detector in front of the other, tap some of the energy off, you think, well, I'd have to see a whole photon going on to do that. I'm getting a 2-for-1 effect. That's what's so sensational here. I'm getting one at a time emitted and going to 2 detectors to make it go click. And you think, well, how can that happen? You're not going to get it with particles. That's what's so sensational about what I'm doing.
So you split the gamma ray.
I'm splitting the gamma ray, but I'm getting 2 of them when there should only be 1. The way that would happen is by this accumulation hypothesis that I've been mentioning before, that it's a threshold. I'm showing the threshold property. And that's how to see through the illusion of wave particle duality.
All right. So as far as you know, light can be explained strictly as wave phenomenon.
Yes, but there is something particle-like going on in the conversion between matter and light. There are thresholds where it's emitted in a bunch, and then thereafter it goes classically. And then the opposite happens. It could be absorbed until it reaches a threshold in the detector or in anything absorbing, and it goes click. And so there's something true about the particle property. But if you see it in terms of threshold, you won't be stuck in wave particle duality.
Well, I guess my own personal opinion is that as light travels, it kind of looks like a particle because it travels in a distinct wave packet, like a broomstick, and that's something we don't normally associate with waves. But so I guess I would try and assert that the way light travels in a packet, that is kind of particle-like, and that
that's just your model talking. That's the model of people interpreting the whole list of experiments, like the photoelectric effect. They apply a particle model. Compton effect, apply a particle model. Well, there's another model. So you don't need to picture a particle going across to explain those experiments.
No, but I'm trying to just make the distinction that as it travels as a wave packet, which contains a fixed quanta of energy.
That's your model talking to you that is traveling in a wave packet. That's your understanding of other people's experiments talking to you, saying it's traveling in a wave packet. That's when you do that, you're throwing away the wave properties by calling it a particle. That
No, I don't believe I am. I mean, I'm calling it's a wave that travels coherently.
if you're calling it a wave packet that holds itself together, you might as well call it a particle. It's about
No,
whether
because I think that's a big distinction.
it's about whether it holds itself together. Does the wave packet hold itself together, or is it spread? You can have a wave packet that holds itself together. Well, if it does that, you might as well call it a particle. Like
No, I would disagree with that.
let's define what a particle is. Is a galaxy a particle? Sure, it is. Is the Earth a part? The Earth is a particle. They're not point particles. Point particles are different. But you can have a particle made up out of a wave internally. Like
No,
ocean
actually, I
waves.
don't think you can. I mean, that's actually a big theoretical question as whether you can make something that looks like a particle out of waves. And a lot of theorists would say that that's how they conceive of what matter is, that it's some kind of standing wave. Now, I would personally disagree with that.
There are ways of making of theorizing and understanding that a particle is made out of a wave packet that holds itself together. And that would be a particle. It holds itself together. But it doesn't always hold itself together. It could spread out. So with matter, what I'm saying is going on is that there are two states, that it could hold itself together or not. But with light, it just does not hold itself together at all. That's the model that I've ended up with. And there's a long explanation for that I have. But as far as saying, well, can you make a particle out of a wave and have it hold itself together? I don't see the problem with that. It's called a soliton. There's a lot of theory that people put together where you can make waves just circle on themselves internally and it'll hold itself together. All right, let it hold together. Does it always hold together? What if it spreads all over the place and acts like a wave? Then it's not holding together. Then it really lost it. So you'll see wave properties and particle properties depending on how you look at it. But then there are some experiments where you'll see both at the same time. If you take a light beam and have it diffract all over the place and put a photomultiplier tube on it, you'll see, oh, well, the photomultiplier tube made clicks and it did make an interference pattern. Right there, you see both at the same time. Then you're stuck with duality. And then you're wondering, well, what's going on? Well, that's why I went through all the trouble to make this experiment.
Well, I think that is probably a distinction between different theorists. For myself, I think that particles at their fundamental are actually ponderable and do contain what we would call a substance. So, and we would make a distinction between like stuff like, my mouse here, which is made out of matter and particles, versus the sound waves that are emanating from my mouth, which are waves. And I would put a very, very distinct difference between those two. So, I mean, it's a matter of what you believe, of course, but I'm strongly opposed to the idea that matter is somehow composed of waves.
Yeah, yeah. Well, that's too bad. You can have waves hold themselves together, uh, but I'll, I'll let somebody else go on.
Yeah, does anyone else have any opinion on this whole thing about can
Yeah,
matter be made out of waves, or do you or do you not believe that?
okay, I think matter is capable of being waves. And I go back to ether cells, solitons, I don't care what they're called, but they are cells that are made up of particles that are hooked together, and they can vibrate, probably vibrate in many ways, probably account for um, the idea that you came up with, Franklin, that space may be quantized, because they're all the same. They can vibrate in many different ways, but they have a set number of ways they can vibrate because of their structure. But if one can vibrate, you can call that a wave. If it can vibrate and hit its neighbor, then it transfers energy and on to the next, and you can call that a wave. And you can call groups of vibrations waves, as say on a violin string, or in many other ways that we can make waves. We can make waves with our voices. The molecules of air are flexible, and they can expand and shrink, and they can hit their neighbor, which is exactly what they do until they ultimately, the vibrations get carried on to your neighbor's eardrums. So a so-called particle, which I will call an ether cell or soliton, can be in effect a wave. It's the cause of a wave. It can vibrate, and it can also account for um, uh, the what is that expression you use to explain what can happen in space? The I'm sorry, I forgot that word. I said it a minute ago. In any event, you you've got the combination right there. If you accept of there being a flexible cell, because it can vibrate and it can cause other things to vibrate. So you've got a combination of vibrations, which are waves, transferred vibrations, which are waves, and it's happening through something ponderable that is real, a cell. Anyhow, that's my thought.
That sounds a little bit like string theory, where somehow they are basing everything off of these vibrating strings. I was reading a recent article about saying that there's this prize, the Breakthrough Physics Prize. Have you guys heard of this? Apparently a $3 million prize for fundamental research in physics. And it was won this year by a string theorist. Apparently it's been won for the past 3 years by string theorists. And then I go read all the comments in there, and they're saying, oh, yeah, well, it'd be nice if they could actually come up with something experimentally provable. So how could that be fundamental if it hasn't led to any practical demonstration?
I am not an adherent of the string theory. I think what I just said and what I just described is those are my thoughts. And if there are ether cells and they are made up of particles, yes, they got to find some way to hang on to each other so that you got something that can vibrate, just like a bell can vibrate, because you got things that are connected to each other and they can vibrate within that bell. But to call it a string theory, I would need a lot of convincing to accept that what I've just been describing is in reality the string theory.
Please tell me about this prize. I want to apply for it. What is this $1 million prize you're talking about?
Okay, let me see if I can go find the website. I believe I have it here. $3 million prize, which is sponsored by some Russian guy.
Milner?
Let's see
Yuri-
here. I'm going to put it up on the screen here for you. Let's see here. So this is the Fundamental Physics Breakthrough Prize. And so this is founded in 2012 by Yuri Milner. Is that who you're talking about?
Right.
So you can apply to him and maybe you'll get $3 million.
I'll do my best. Thank you.
Seems like an easy way to get $3 million. Show that light is purely a wave phenomenon. I think that would be actually that would be more interesting than anything the string theorists could have to say.
That's right. They don't have an experiment and I do.
Yes, you have an experiment. So I could clearly see coming up with an accurate description of the nature of light. It'd be more fundamental.
Thank you.
But there you go. So there's more than the Nobel Prize. Now, how much do they get for the Nobel Prize? Is that about the same amount, or is it more?
No, it's less than $1 million.
So the Nobel Prize gives you less than $1 million, but this prize gives you $3 million. So it's worth 3 times as much as a Nobel.
Well, look, I'm not doing it for the money anyway.
But obviously this board is controlled by the string theorists in the mainstream. So good luck with that one, I suppose.
Right.
So how do the nominations work on this thing? So nominations for 2017 are closed. Oh, well, I guess you're going to have to work on it next year. And let's see here. I think they have a picture of the trophy. There's the picture of the trophy, Breakthrough Prize in Life Sciences. Wow, they couldn't even center the font on that thing. Okay. And let's see. So when do they open up nominations on this thing? Obviously sometime before December. And how do you nominate? Maybe they have contacts. So I would expect they would have an application here or something, but I don't see it. Otherwise, we would all send our theories to these guys and they would probably blow us off. But yeah, that is the Breakthrough Prize thing. I heard about this. You guys might be interested in this. I've discovered this in what's called physicsworld.com. And every week they send a summary of things that are going on in the world of physics. So the first thing they have here, this is a summary. They've got some things about vibrats. So let's see, let's look at the December 2016 issue. So they've got something about silly putty. And they have something about a sonic lamb shift. This dark matter is smooth. We had some discussion about what on earth dark matter was. And they're saying that it's smoother than they thought it was. They think it was lumpy. Now, considering that we don't even know what dark matter is, how can they determine whether it is smooth or lumpy? So that's an interesting question. And what else is going on here? Tiny device pumps out 1 electron at a time. So this might help us with our experiments to determine whether particles, which we think electrons are, is actually a particle or a wave. If we can actually pump out one of these at a time, so that would be like generating one things at a time. So if Eric could use this device to pump out one electron at a time, but if he managed to show that he could see 2 electrons come out, then that would probably confirm the wave. I mean, actually, well, yeah, that would confirm the wave nature of an electron, I would suppose, right?
Well, let me show you another thing. It turns out that I did the experiment with matter. I did it with the alpha ray. I'm trying to give a close-up of the experiment that I did. I don't know if you can see it or not. There are 2 detectors facing each other, and in between there's a radioisotope of americium. It puts out the alpha, what they call the alpha particle, which is helium. And so it's one at a time, the same way, but it's hard to see because I have tape over it. There's a gold foil in between the 2 detectors. The alpha will split and go to one detector. Usually it goes to one detector or the other. Usually the alpha will either go through the gold foil or reflect off of it. But sometimes it goes to both. I'm able to see this 2-for-1 effect with the matter wave, just like you said. I've already done it, and it's documented on my website. And so I could see this threshold property with the matter wave, with helium, with the alpha ray. So I've spent a few years doing this experiment. I don't know if you can see it. It's a small bell jar. I put my hand over so you can see the size.
Yeah, we can see that there's something gold inside there.
Right, the gold is the detectors. Let me pull this off.
So that would be confirming that that even matter like the alpha particle can be split apart and double detected, kind of confirming the wave nature of even matter.
That's right. Here's with the bell jar taken off. Right, so the gold things are 2 detectors facing each other. There's also a layer of gold in front of one of the detectors. And the alpha ray source is attached inside this bell jar. And so I'm showing the alpha particle is not always a particle. And so the trick is to see, well, did it go to 2 half particles or not? We know it could do that kind of thing, like 2 deuterons. Well, there's not enough kinetic energy to split the deuteron. I'm working at 5.5 MeV, and it takes 14 MeV to split the helium nucleus into deuterons. But nevertheless, there are different ways to do the experiment. I've done it a bunch of ways. So usually it splits into 2 halves. It does often split into 2 halves. But you have to define the binding energy like I just mentioned. But then if you look closely at the experiment and see, well, how often does it do 2 full pulses where it gets 2-for-1? It could still do that. And it's like 5 times accidental chance. So I'm still able to split the atom like a wave. We're calling the helium nucleus, calling it an atom. So I did this beam split coincidence both ways, with matter and this one. get a close up. Trying to get you right inside the chamber. See what this experiment is.
So what are you using to split the alpha particle? Is that just a gold foil?
That's right. For the alpha, it's a gold foil. It's gold leaf. And for the gamma ray, the best way to do that is with a thin detector. But I've done it with materials as well. The experiment that I have going now, it's a thin detector in front of a thick detector. So it's done differently depending on matter or light. But yeah, there's a gold foil there for the matter wave experiment in front of the detector. I'll go to the other side. You'll see what the detector looks like. So, and it's done in a vacuum chamber. So the way I did is I took apart a smoke detector to get the americium, and I did that test also to see that there's a coincidence test that you do to see if it emits one at a time. And that's an important part of this argument. The nuclear physicists know that it emits one at a time, but I test these things independently anyway, both for the alpha ray and the gamma ray. So here we have a situation where it's supposed to, where we see it emits one at a time, and then we get two at a time. We compare it to chance. And then you'll say, well, what is this chance? The chance equation is what's used in all these experiments. That's how they are able to see all the level diagrams published. It's a very common thing. And so I'm not doing anything different from what other people are doing by comparing to chance. And but the way I do it here, you get to see everything. You get to see the timing histogram of how these pulses come together. And it's making a peak. That red thing in the middle is, try to get this. There's a timing histogram peak that, there we go. So any peak in this histogram defies chance. But I measure it. I add up all the pulses and the numbers. Let's go up here on the counters. This is how fast the gamma rays are going through. So this is the thin detector and the thick detector. You see it's coming rather slowly on the thick detector, but it's still coming through. So it's sort of a slow experiment. But when you do the numbers, nevertheless, it all defies chance. So another part of the argument is to look at the pulse heights. Say, oh, Eric, are you looking at full pulses? These are the full pulses that are characteristic of the gamma ray I'm working on. And I take pulse height histograms all the time on this to see that they're not half high pulses, to see that they're all valid. So, and then I even do a histogram of the sum of the two pulses to see how they're working together. I'm looking at both energy and time. Well, pulse height is proportional to electromagnetic frequency, and it's also proportional to what they call the photon energy. So that's a big part of my argument. That I'm looking at full pulse heights. Coincidence to get 2 for 1 to defy quantum mechanics.
So getting back to the matter experiment, so your americium, which we got out of the fire detector, so that, generally speaking, doesn't emit a single particle at a time, right? But you said that you characterized what is coming out of that emission.
It does emit a single at a time.
Does it? The fire
Yes.
detector element that only emits a single alpha at a time?
The rate is high. The count rate is high enough. I mean, there could be different atoms that put close together emissions, but when you look at the pulses and on this kind of histogram I was showing, we can see that they come together at times that are but they're usually by the chance rate when they're emitted. They're random times that the detections happen, and the way you test that is similar to this, where you have 2 detectors that are sandwiched together, but you have the source so that it can go to both detectors. So when you do this sandwich the sandwich test is about telling, well, does it emit one at a time? Well, when we do that, we get chance. There's no peak in the histogram. But then you change the source, so you shade it so it only goes to one detector. And then you get to see my experiment. So where you aim it to one detector and you see if it goes through the gold foil or if it reflects. Then you see this test with chance. You see, then the peak in the histogram comes back. That's what's so. You could see the difference between the true coincidence test and the on-quantum test. Now, you think this should have been looked at a long time ago. Well, it's not an easy test to do. You have to know what you're doing. There are plenty of isotopes with gamma rays tried where you will see chance. It will look like a photon. And I've had to sort out, well, when does it defy chance and when doesn't it?
I was kind of curious, where did you get all your equipment? I mean, it looks like you've got $250,000 worth of lab equipment sitting there.
I even have more. I have a whole optics table here where I'm working on an experiment to resolve the secret of life, where I made my own lasers. And, I don't know if you can see anything, interferometers. So it's a lifetime of good luck, so to speak. A lot of eBay work, help from my friends, family, all different ways. I've been very lucky in being able to do this.
Yeah, because I normally don't see equipment like that except in the university laboratories. I mean, this is your house, right?
That's right. This is the living room of the house.
And it looks like the middle of a very, very sophisticated scientific laboratory, the living room.
It is sophisticated. Let's see. There we go. That's the optics table. So this is where I built my lasers. So that's another experiment that is not giving me results yet. I'm still assembling it.
What kind of experiment are you running there?
I'm gonna mix two lasers together to get a terahertz beat. And I don't want to say everything, but let me unearth this. This is a here we go. That's a scanning Fabry Pro interferometer. I can even turn it on. It'll take a few minutes to turn it on. I wasn't planning on doing this, but I know a lot about light and interferometers to make all this work. To
So is that something you can pick up on eBay?
wow. I made these interferometers.
You made them.
I made these instruments from components like mirrors and motion stages. And I made this laser. It's a tunable narrow band infrared laser. So I'm good at building things. So I don't know, maybe I shouldn't have distracted you, but I have a whole lab of several experiments going on. But this is the most important one, the gamma ray experiment. That's what's running right now. But I did want to clue you in about the electron, like you mentioned, because, right, it's much harder to do the experiment with the charge wave with electrons. I thought about doing that, but that's even more difficult instrumentation. But I was able to do it with the alpha ray, which in a way is even more sensational because it has 1836 times the mass. No, that's the ratio of the proton to electron mass. There's a lot more mass. So this is the more important one. This is the one that works the best, where there's gamma rays. The gamma ray source is way in there. It's in a block of lead, so it's aiming. And this is the thin detector. It's really difficult to see what it is. There's a thin detector further back, and then there's this thicker one. The gamma rays will go through, and if it was a photon, the model of quantum mechanics, all the math of quantum mechanics, would say that it should go to one detector or the other, except by accidental chance. But it's not just math. There are other people's experiments, and I've had to deal with that. I've had to explain why is it that other people have done this experiment with visible light, and they get the opposite result. And that's why everybody thinks light is photon.
Well, how do you explain those experiments then? If you use regular optical light, you get this photon behavior. But if you use gamma, you get, this wave behavior. So how do you explain what the difference is?
Right. It's that when it's emitted from radioactive decay, it's more pulse-like, and that we're able to set off detectors in a pulse-like fashion. It's more pulse-like emission from the gamma ray that I'm taking advantage of. to do. So if I was to look, let me backtrack. It's also the photoelectric efficiency of the detector. In my writing, I outline all this. At 88 keV for cadmium 109, photoelectric efficiency of sodium iodide detectors is higher than if you look at cesium 137, which has like a 600 keV gamma ray. So usually they use higher energy gamma ray, higher frequency gamma ray. And they'll say, oh, it goes to one detector or the other randomly, and they'll say it's a photon. And they won't see this. You have to know where to look. So it's about photoelectric efficiency for the combination of detector and source, and also just understanding that it's a pulse-like emission from the source. And there are a few other things. So there are reasons why it's a difficult illusion to see through, to see whether this loading theory can work. Now the other problem with the loading theory is people have looked at that. That was the first model that came up. When Lenard was doing the photoelectric effect, he was doing something very similar. It was called the trigger hypothesis. That was, and then Einstein got a hold of Lenard's data through his wife, and Einstein's wife applied the photon model. But there are many other people who worked on the loading theory. Planck and Sommerfeld. Sommerfeld did a whole theory on this accumulation hypothesis. There are many great people who worked on it, but it fell out of favor. There's a historical analysis I did. It's in my writing.
Okay, so we're getting close to the top of the hour here. So I'm going to try to do a little summary of what we have discussed today in our science chat, December 17th. So we've been looking a lot at the work of Eric Reiter, and he's been showing us his experiment, which demonstrates that that the gamma ray can be split, and that can be explained by showing that the gamma ray has a light wave like particle which can be split, something that would go along with our hypothesis that light is strictly a wave phenomenon. So we were discussing, is light really a particle or wave, and the various experiments that have been put forth to say that, hey, light is a photon, and hey, light is a wave. And we did have some discussion about whether the medium that light travels through would have an effect on this. We'd also discussed about the photoelectric effect, which is basically what these detectors use, and that we did have Bill Lucas saying that that the photoelectric effect does require a crystalline structure, so that may be some clue. Since I think that the argument is that